Okay, today we're going to move on a little bit. I started marking, I didn't have a chance on the weekend, but I had a look at some of the frictional stuff of your lab this morning. Some of you have a little bit of fix-up to do. If you didn't finish it, you need to get that in. I think everyone's done all the data. I don't think there's any group that isn't that. I'm still missing a stopwatch, you guys. I sure wish I knew where it went, because it was your class that lost it. So if you put it in a drawer, or if it's in a pocket or a binder or some other, I would like it back. But, you should have on your desk there a sheet with these example questions. These are from the textbook. We're going to talk about inclined planes with friction today, and it's one of my favorite lessons because I get to show you video from 1970 something or other, Evel Knievel attempting to jump the Snake River Canyon. One of my favorite things to show people because it's so 1970s. But let's begin with this one here. A girl sits at the top of a frictionless, snow-covered hill on her inner tube. If the hill is inclined at an angle of 25 degrees to the horizontal, what will be the girl's acceleration due to gravity? So let's figure this out. Okay, so let's have a look here. Let's first of all draw a free-body diagram. Now, one of the things you had to do on that lab is draw a free-body diagram, and there's a few of you that need some work on that. So this is a good chance for me to remind you of what's going on here, right? So we've got our hill here, and we've got our object. It's a girl on an inner tube. And we've got gravity, weight force, acting straight down. And we've also got the complement of that, we've got the normal force acting, Fn. We've got that acting perpendicular to the surface, right? But because they are not equal and opposite, we're faced with a net force, and that net force is Fd, the force down the plane. Now, are there any other forces present here? Are there any other forces present here? The answer is no. If there were friction, it would be where? It would be there, but there's no friction. Right? Okay. So what will be the girl's acceleration due to gravity? Well, the only force acting in the direction of motion is Fd, right? So what is our value of Fd? Fd is equal to mg sine theta. And you know what? I'm going to move this over here so that I know that I have room. What's the mass of the girl? Well, we don't have it. What are we going to do? Well, let's just leave it as an m for now and see what happens. Okay, you can do that, right? We're just going to leave the value m in there. 9.8 times the sine of 25. Hey, did you guys see? Okay, so 9.8 times the sine of 25, so we're going to have 4.14, and we're just going to leave the value m, because we don't know what it is. Now, sometimes when this happens, when you're given a situation like this, sometimes the m will cancel out, right? So that's not meters, that's the variable m, right? But we're trying to find the acceleration. F net is equal to ma. Oh, hey, this is looking promising, because 4.14 m is equal to m times a, which is what we're solving for, and the m's do what? Cancel out, and so our acceleration is 4.14 meters per second squared. Yeah? It'd be like that day when I was about 12 years old, Randy Dreger lost his spleen on the tubing hill.
Randy Dreger lost his spleen.
Yeah, we were all... All right, now some of you may have realized that I've already told you on a frictionless surface, acceleration is equal to g sine theta, right? Which would be 9.8 sine 25, which is exactly the same as this thing right here. Right? I wanted to see if anyone would say anything as I was going through. So I'm just reminding you that on a frictionless surface, A is equal to G sine theta. Okay? All right, so let's look to example number 2. Now, when I was a kid in the Randy Greger days, Evel Knievel was like the coolest guy in the world, pretty much, right? He was the daredevil. His son is Robbie Knievel. This is Caesar's Palace. It looks nothing like that now. This was 1977 or whatever. He jumped over the fountains at Caesar's Palace. There's video of it. He pretty much broke every bone in his body when he landed. He's driving his motorcycle up a ramp inclined at 30 degrees from horizontal before jumping over a row of cars. This is just a picture. If there's a constant frictional force of 1,000 newtons on the ramp, determine the force that the motorcycle engine must apply to accelerate up the ramp at 1/3 G. Okay, that's what that means, 1/3 G. Assume the mass is 250 grams. So first of all, what the heck does 1/3 G mean? Yes, 1/3 G is 1/3 times 9.8. Quite often, acceleration is measured in G's. So we're going to take that 9.8, we're going to divide it by 3, and we're going to get 3.27 meters per second squared. That is our acceleration. 1/3 G. And we need to know, we're trying to find the force that the motorcycle engine must apply. So what are we solving for? We're solving for the FA. Let's draw a picture. Here he is going up the ramp. There is an applied force up, which is what we have to solve for. What's slowing him down?
Friction force and FD.
Yes. FD and friction. Is there going to be a net force here? Yeah, because he's accelerating, right? So this FA is actually going to be significantly bigger, isn't it, right? Okay. Well, let's find out what that net force is going to be. The net force is mass times acceleration. 250 times that 3.27 value, which is 816.7 newtons. Now, is the force of the motorcycle engine going to be more than 816 or less than 816? Or equal to 816, I guess? The net force is 816. Way more? Dan, why do you say way more? Yeah. The sum, the vector sum of FA and FD and FF has to add up to 816 up the ramp, right? So this FA is going to be way more than 816, exactly. So we need to figure out what FD and FF are, right? FD is equal to mg sine theta. We've been working with that for a few days now. Say again? This number here?
Yeah.
What's it supposed to be? Oh, okay. Oh, you know what I did? I took 250 times 9.8 divided by 3. That's how I got my value. What do you want it to be? 817? Okay. So this value here is going to be 250 times 9.8 times the sine of, what's my angle here? 30. 250 times 9.8 times sine 30. I think that value is 1225. Did I get that right? Yeah? Okay. Now there's also FF, but how much is the FF? Well, I think it told us, didn't it? There's a constant frictional force of 1,000 newtons. So they're just going to say FF is equal to 1,000. Right? Okay, so now I think I can write, I'm almost done. F net is equal to the applied force plus the friction force plus the FD. our net force was 817.5. The tricky part of this one is knowing what you're solving for, really. FA. The FF, now 1,000 or minus 1,000? Why negative, Shelby? Going the other way, right? And the 817 is positive, right? And the FD would also be negative, wouldn't it? Okay. We had a very similar question in grade 11, I remember, with a truck that was just on the flat surface. So the minus 1,000 and the minus 1225 are going to go to the other side and become positive. And I'm going to have 817.5 plus 1,000 plus 1225 is equal to my applied force. And as we predicted, the applied force is going to be significantly more. I get 3,042.5 newtons. So I guess Evel Knievel has to make sure that his motorbike could actually provide that kind of force, right? They're probably more interested in how fast it's going, right? Would be how they would do it. Now, do you think back in 1976 or whatever year that was that he jumped at Caesar's Palace, they actually had a guy figuring out this stuff? You would think so. Based on what I know, I'm guessing they didn't. I think they just winged it. They probably had some kind of general rough idea, but they didn't do a lot of this. And you'll see in the video that I'm going to show you the lack of planning that went on in the 1970s. It's really lousy video, but it's funny. Okay? Now, the question in the book is pretty easy. So I've added on this question here. So it says, suppose rather than 1,000 newtons of force, suppose that the frictional coefficient is 0.15. So let's just finish this. I promise you I will show you the video. Right? So I'm just going to redraw this here. You probably don't because you've got it right in front of you. FD and FF and FA, right? So we know our net force is still that number. The net force has to be this 817.5. We know our FD remains 1225. But how do we find the friction force if the frictional coefficient is 0.15? You need the Fn, right? So we're going to do that. So I'm just showing you this because you're going to run across this. So Fn is equal to mg cos theta, which is going to be 250 times 9.8 times cosine. Is it 25 or is it 30? I think it's 30. I get 2121.8 newtons, but that's just the normal force. That's not the friction force, right? 2121.8. Good idea? Yeah, okay. Mu equals FF over Fn. The mu value is given to be 0.15. We're solving for friction force. Fn is this 2121.8. So that value times 0.15, 318.3. Okay? So now it's just an alternate way to get that friction force, really, right? If you're given the coefficient instead of that. And then we're just going to do this step again. F net is equal to FA plus FD plus FF. This F net was 817.5. We're solving for applied force. FD was minus 1225 and FF is now minus 318.3. This time I get 23 60.8 newtons. 2360.8. I do want to point out that if you want, you can kind of combine these two steps, because FF is equal to, mu is equal to FF over Fn. If you want to just say that FF is equal to mu times Fn, and Fn is mg cos theta, and I think this was actually on your lab sheet, right? FF is equal to mu mg cos theta. If you want to just use that as a way of combining those two steps, you can do that. There are some textbook questions that are pretty good. They're challenging, but they're good for you. 196, numbers 1 to 4, 224, 6 to 10. You should probably do at least one of each set. 224, 6 to 10. 196, 1 to 4, 224, 6 to 10. So that's 8 questions altogether, I think. 6, 7, 8, 9, 10. No, that's 5. That's 9 questions. So you should probably do at least one on each one of those, just as a practice. Okay, so the question reads, a 100 kilogram commuter, which is just like a person going to work on the train, right? 100 kilograms, they're a large person, standing on a train accelerating at 3.7 meters per second. 3.7 meters per second squared. So they're accelerating. So when you're standing on a train, right, like if you were standing on a train and you were wearing rollerblades, what would happen? The train would accelerate underneath you, and you would end up rolling kind of backwards, but you'd actually stay in place relative to the ground, right? Okay, but the person isn't on rollerblades. They are wearing regular shoes, but what actually holds them in place? Friction. Okay? So what coefficient of friction must exist between the commuter's feet and the floor to avoid sliding? So we're looking for mu equals FF over Fn. Can I figure out what Fn is? Yeah, that's going to be Fw, right? The friction force is what is holding them in place, but it's also what is actually, it's friction that's actually pushing him forward, right? It's the friction force between the person's shoes and the train that's actually accelerating them. And that is indeed, just on the tester, is actually what the net force is. So what is the net force on this person? The net force is mass times acceleration. This is the reason why it's a 100 kilogram person, because you can multiply without using a calculator. So it's 370 newtons of force is acting on the person. And what is providing that? Friction. So all we got to do now is find our normal force, which is equal to our weight force, which is 100 times 9.8, which is 980. If you want to make it negative, you can. So you get a mu value here of FF is therefore my friction force is 370 newtons. And I realize that probably some of you still don't get that. Why? It's friction that's pushing them forward. It's friction that's actually, friction is opposite to the motion, right? Well, the person, if there was a frictionless surface, the motion would be backward. So it's actually friction that's pushing you forward. It's really no different than when you're walking down the street, right? As I push off, right? As I push off here, what's pushing me forward? Friction, right? Friction between my shoe and the floor. So same idea, except they're standing still. So the mu value is 370 over 980, which is 0.378. Sure. Which is like double wood on wood, right? So I mean, any train, that's the, you'd have to have at least that much friction. If you had more than that, then it'd be no problem, right? Most trains are not made with slippy surfaces. They're going to be made with a rubber floor or something like that, so people can stand and hang on. People usually ask me about that question, so I'm glad that it came up, Braden. Thanks for asking. Okay.